last week of class. Yeah, you ready? Lecture 36 today. I'm going to treat lecture A here today as a review, essentially, for the final exam, as far as field theory goes. So lecture A, and probably part of lecture B, will be essentially your main review of field theory. I do want to introduce Galois theory at the end of lecture 36 here. And then Wednesday, in lecture 37, I want it to be pretty much all Galois theory. And it's a tough subject, but we are going to just focus on the basics and examples. But I think in doing that, it'll have the added benefit of allowing us to review group theory. Because Galois theory is all about using group theory to understand field theory. Kind of an amazing thing. Okay? So that will allow us to review some group theory at the same time. And then on Friday, it's pretty much going to be all review of things that I did not have the time to review both today and Wednesday. Okay? All right, we have to go back to a story from my past here quick again. So we talked about that guy who was the kind of the bully who laughed at me at baseball and said he was going to bite my ear off in high school. And as I sent you a message over the weekend, he actually was somewhat famous. He's got his own Wikipedia page. And I did look up some YouTube videos of him. And there are YouTube videos of him wrestling, professional wrestler. But the amazing thing, I mean, Wikipedia could be wrong, of course, but it said he was 5 years older than me. Yeah, he must have gotten held back 3 times in school, because I thought he was only 2 years older than me. He was in 12th grade when I was in 10th grade. We did, in the past, 60s, 70s, and 80s, used to actually hold people back if they didn't pass classes in school. Now they don't really hold people back, but that must have been what happened. I did have to play football with him, too. Oh, it's not as bad as it sounds. He was on my team. So it was not as bad as it could have been. So my football story, American football, is that, well, okay, I like football, I like watching it. And 4th and 5th grade, here's the kind of football we played in 4th and 5th grade. I don't know if you experienced something similar or not. Played out in the playground during recess, and everybody was a receiver except for the quarterback. So 10 people going out for a pass. You know, whoever's rushing the passer has to count to 1,000 or something. But everybody's going out for a pass, and so I'd play and I'd go out for a pass, and they never passed it to me. Because they knew, well, every once in a while they'd actually pass it to me, but I'd drop it. So that's why they never passed it to me. So not only was I small, I was also slow, I was uncoordinated, and I dropped the ball. But then I told my mom and dad in 6th grade, hey, I want to play football. And they're like, what? Really? They were really scared for me, I think. I thought they wanted me to play football, actually. They let me play. I weighed 68 pounds in 6th grade. Okay, that's how small I was. The average football player in 6th grade maybe weighs 110. I weighed 68. The coach was scratching his head, wondering where he should put me on the team. They had to let me be on the team. And he's like, okay, where can he do the least damage? I'll put him at safety. Okay, so I was a safety. And I would be on kickoff coverage as well. And he knew I wouldn't get hurt because I was so slow that I couldn't make it down in time. But anyway, I was a safety and I was very small and I couldn't really tackle somebody one-on-one. I was slow too, like I said. But when they got down, I would, make sure they were down when somebody else tackled them. I did have one good play though. I did actually intercept a pass once and I didn't drop it. It was amazing. The quarterback threw it right to me. I caught it. I was tackled right away. I didn't fumble. It was astonishing. I was amazed that I didn't drop it. Either case, both when I caught it and also when I was tackled. Our team actually was very good because that guy was on the team, partially. 5 years older than everybody else, I guess. And we were 8-0. But anyway, I did have one good play. So that's my football story. All right. So lecture 36A again, we're going to review field theory. So we want to try to put all these pieces together, okay, in our minds. That's what this is all about here. Phrasing this as questions and answers of different things you could ask and try to answer in basic field theory. So we've talked about field extensions, right? trying to take a given base field and extend it to some bigger field that would hopefully have zeros of the given polynomial that might be irreducible over the base field. And so you could ask the question, given a field f and a non-constant polynomial f of x in the ring, right, that's a ring, not a field, in the ring of polynomials with coefficients in f, does there exist an extension field, a bigger field, E of f, in which f of x has a 0? What do you think the answer is? What have all of our examples seem to be indicating? The answer is yes, and you can prove it. And that's the content of the very first theorem in chapter 20, fundamental theorem of field theory, also called Kronecker's theorem. In this situation, yes, there is some extension field in which little f of x has a 0. A 0. Maybe just 1 0, maybe more than 1 0, but at least 1 0. The proof is not something that we did in class, and what I've been trying to emphasize in this field theory stuff is not so much the abstract theorems as much as the examples. Well, and illustrating the abstract theorem with examples, not so much proofs. And the proof is actually not super hard, but we've really been more illustrating the proof with examples. Here's the idea. Look here first. Say, well, okay, f of x may not be irreducible. It might be reducible. You know, it might be quartic, fourth degree, and you might be able to factor it as a product of two quadratics. Yet it still not have a 0 in f. But it's got some irreducible factor, call it p of x. Create that factor ring, right? Take we've done this a lot, take the ring of polynomials with coefficients in f and mod by this ideal generated by this irreducible, and since p of x is irreducible over f, what can you say about this ideal? It would be a, what kind of ideal? It starts with an m. Maximal ideal in this ring. And therefore this factor ring would be a ring, integral domain. It's more special. It starts with an f. This factor ring will be a, come on. Oh no. Field, yes. This will be a field. That's what I'm calling it. I'm calling it E, and it's going to be an extension field with capital F. This field can naturally be thought of as an extension field of capital F. Is it technically really a set that contains F? Actually, technically, no. The elements aren't the right types of elements. You know, F, where's F? Well, I guess it's right here. F is an arbitrary field, could be a finite field, could be an infinite field. Imagine it's Q. So its elements are numbers. The elements of this field are not numbers, they are technically cosets, right? This is a factor or quotient ring that happens to be a field. Its elements are cosets. However, there's a natural, sometimes this would be called an embedding. There's a natural function from F to E. There will be a homomorphism, a ring homomorphism, that's one-to-one, but not onto. One-to-one ring homomorphism. And actually, since F is a field, you could call it a field homomorphism too. That would be okay. Not onto. What is it? It's a natural way to essentially take F, imagine E is over here, and embed it. Embed in E its image would be the thing that E is really an extension of, that's isomorphic to F. But what is this mapping? Well, take an arbitrary element of F, and the most natural thing to do to make sure it's in E, which is this, is to map it to the left coset of this ideal in this factor ring with A as a representative. That would be the most natural thing to do, and in fact that is what you do. That would be a one-to-one ring homomorphism that embeds F in this factor ring E, that is a field, and therefore E can be thought of as an extension field of the original. Okay, so it's sort of a conceptual sleight of hand, so to speak. This is the way algebraists think, though, is even though technically F is not a subset of E, it's got an isomorphic copy of itself inside E, and therefore we can be justified in saying that E is an extension field of F. Here's another question. Is such an extension field unique? When we first define extension fields, we say, well, okay, that's a different question. The answer here is no. There are plenty of extension fields of the base field that might have a given element as a zero of the given polynomial. For example, both Q of I and C are extension fields of Q containing a zero of x squared plus 1. And there are infinitely many other choices as well. I could go, as long as I include I could go Q of I, comma, square root of 2. Just doing sort of random things here. I could join the square root of 3. All of these are extensions of Q, the rationals, that contain a root of x squared plus 1. They all contain I. Okay. Q of I is the minimal one. It's the minimal extension of Q that contains I. It would be the splitting field for x squared plus 1 over Q. But there are plenty of extensions that contain a zero of x squared plus 1. Remember, we're splitting fields too. It's always with respect to the base field. Qi is the splitting field for x squared plus 1 over Q. Ri, which would happen to be the complex numbers actually, is a splitting field for x squared plus 1 over R. So the answer whether something is a splitting field is always with respect to some base field. Okay, the answer can be different. So this is review. This is all stuff that we've talked about, and you should know. These are factual things you should know for the final exam. You should be able to answer true-false questions about these kinds of things. Do calculations like we've been doing with related to these things with finding splitting fields and doing calculations in the splitting field in the extension with coset manipulations like we did last time, where you have to end up using synthetic division or long division to help you. As another example, this is kind of an oddball example. I took it out of the book. It's a little strange. Because there are some things to verify, and it seems like it's pulled out of thin air here. Start with the polynomial here. F of x equals x to the fifth plus 2x squared plus 2x plus 2. Fifth degree polynomial. Consider that to be a polynomial in z3x. So consider those coefficients to be in Z3. It turns out you can factor this polynomial in Z3x as the product of these two things whose ideals we're modding by there. That's something you should be able to verify if I put this on the exam. You should be able to verify if I told you that this given polynomial can factor in this way. How would you do it? Use long division. Divide f of x, divide this thing, for example, by x squared plus 1, you should get a quotient equal to that and a remainder of 0. And you would have to use long division here, not synthetic division, because synthetic division is only for dividing by linear factors, not for dividing by quadratics. Maybe this is worth doing as an example. So let's do it in terms of long division. Now, with long division, you don't have to put space when you don't have, well, in this case, fourth and third powers of x. But it doesn't hurt to put space. It might be helpful. Let's go ahead and do this long division to confirm this. This marker's starting to die in me, I hope. Let's try this one. What do you have to multiply x squared by to get x to the fifth? You got to multiply it by x cubed. Multiply that now. X cubed times x squared is x to the fifth. X cubed times 1 is x cubed. Subtract. With long division, you subtract. Mod 3, so we get a negative x cubed. That's the same as positive 2x cubed, because we're doing mod 3. Run out of room here. What do you need to multiply x squared by to get 2x cubed? You need to multiply it by plus 2x. Multiply, get 2x cubed here, plus 2x. Put the 2x right there. Subtract. The 2x cubed and the 2x cancel. We get zeros underneath these things, so we just get 2x squared plus 2. And yeah, now we'll just do a plus 2 here, and we'll get a 2x squared plus 2 down here. And those subtract to 0, the remainder is 0. And the quotient is, as I said, it would be x cubed plus 2x plus 2. This. Okay, so this, while this example seems like it's kind of pulled out of a hat, if I told you, if I put this example in the final exam, you should be able to verify that. And it turns out then that, well, you have to know these things are irreducible over Z3, and they are. Okay, you'd have to check that. And once you've checked that, you would know these factor rings are actually fields, and would therefore then be field extensions of Z3. And by what we know, the theory, we know these would both contain a 0 of this polynomial. In both cases, the 0 would be of the form, at least one 0 would be of the form x plus the coset, right? That's what I emphasized last Friday, was that whenever you do this kind of construction, one 0 for sure, not necessarily the only 0, but one 0 for sure is the coset with x as a representative. And essentially that was the proof of Kronecker's theorem. X plus the coset is going to be a 0. Could be more, but that's at least one. So these are both field extensions, different field extensions of Z3 that contain a 0 of that. And they're different orders for these fields as well. Think about it here. Here we're modding by the ideal generated by an irreducible quadratic. The representatives can be taken to be linear, right? One less than the degree of the thing we're modding by. Elements of that are going to be of this form, where A and B are in Z3. Meaning there's going to be, what? 3 squared elements. 3 choices for A, 3 choices for B, 9 elements in this field. This is a field with 9 elements. How many elements does this field have? It's not 9. Bigger, what would it be? What's the key? I'm pointing at it. The key is that degree. Take the representatives to be quadratic. Degree 1 less than the degree of the irreducible polynomial whose ideal generated by it we are modding by. Right? These are things we've seen. If you don't remember seeing these things, then, well, you should have, okay? We talked about these kinds of things. You've had examples like this. A, B, and C are all in Z3, so you've got 3 choices for each of those 3 things. You're going to have 3 cubed, 27 elements in this field. Okay? So while these are both field extensions of Z3 that contain a 0 of little f of x, they're not the same. In fact, they even have different sizes. And you can't even consider one of them to be a subfield of the other, because remember also from last Friday that with finite fields, well, 3 is a prime, and there are fields of order 3 squared and 3 cubed. But because 2 does not divide 3, powers there, 2 does not divide 3, a field of order 27 is not going to have a subfield of order 9. Just like we saw a field of order 8 did not have a subfield of order 4. A field of order 81 would have a subfield of order 9, because 2 does divide 4. But a field of order 27 does not have a subfield of order 9. We saw that last Friday. Given a field f and a non-constant polynomial in the ring of polynomials with coefficients in f, does there exist an extension field E of f in which little f of x completely factors into linear vectors, in which it splits? And is there a minimal such field, a splitting field, containing f and all the zeros of little f of x? And based on your experience, the answer should be, based on or listening to me or reading the book, what do you think the answer to this is? Yes. We've been talking about this stuff, right? It must be true. Yes, splitting field exists. If you find an extension with 1 0, but not other zeros of little f of x, maybe you have to continue extending it more to get an extension in which little f of x splits. What's the minimal such one? Don't keep going forever in your extensions. Stop somewhere until you've got all the zeros of a given f of x. It will exist. The proof is actually by induction. Are splitting fields unique? When we first define splitting fields, we say this is a splitting field. The answer to that is, it depends. Depends on what you mean by unique. Algebraics typically answer this yes, if you mean unique up to isomorphism, which is what they usually mean. Technically speaking, there can be different splitting fields that are technically different fields. In fact, we point out in your book, example 6 on page 342 gives 2 different, technically, splitting fields of the same polynomial. But they are isomorphic, and so as far as algebraics are concerned, that's the meaning they usually take. Up to isomorphism, they're the same. Okay. Now, so far what I've talked about today here is the most important parts, for me at least, for you to understand for the first, 6 pages or so of chapter 20. After that, maybe 7 or 8 pages. After that, starting about page 345, chapter 20, I think, seems to get extra hard. And there's stuff about derivatives even in there, and multiple zeros, and perfect fields. And I haven't talked about that at all. I wanted you to read about it at least, just so you're at least a tiny bit familiar with it. But I'm not going to test you on that. Other stuff. Essentially the last 1, 2, 3, 4, 5, 6 pages or so of chapter 20. We are focusing on other stuff. How can we find extensions and describe them, classify them? This is getting into chapter 21 now. Algebraic versus transcendental. Remind yourself what's an algebraic extension. I could very much see the definition of an algebraic extension being on the final exam. What's an algebraic extension? A field extension, E of a base field F, is going to be an algebraic extension if every element in the extension field is algebraic over the base field. But what does it mean for an element to be algebraic? It means, can you finish it for me? An element A in a field extension E of a base field F is algebraic over F if what? Nobody? Probably better put this on the test. What do they want to say? What want to say here?
If A is a zero, it's a non-zero polynomial.
Okay. Yeah. If A is a zero of some non-zero polynomial, not technically not non-constant, it would even be with coefficients in F. If it's not algebraic, then we call it transcendental. So the definition of transcendental is not algebraic. An extension E of F is going to be transcendental if at least one element is transcendental in the extension. What is F of A isomorphic to in each case? And remind yourself what this notation means. This is the smallest field extension of F in some bigger field E, say, containing A. It contains both F and A. If A is transcendental, this is isomorphic to this, and you should know this notation means this is the field of rational functions in X. You should know what that notation means. So ratios of two polynomials are the elements of this. Sometimes called a field of quotients. Which is more complicated. We'd like something simpler. If A is algebraic, then we come back to this thing again. F of A is isomorphic to this factor ring, which is going to be a field when P of X is some irreducible polynomial, and there will be some irreducible polynomial for which these two things are isomorphic. And in fact, we can even take P of X to be the sort of simplest kind of example of a minimum degree polynomial that's irreducible. We can take it to be mnemonic, having a leading coefficient of 1. And there's a unique such polynomial. We call it the minimal polynomial for A over F. There's the vector space description of these elements. I mean, technically the elements in here are cosets. However, as we talked about on Friday, you can kind of dispense with the coset notation and just focus on the representatives, and that's good enough as your field. And if the degree of P of X is n, there's a theorem, actually even back in chapter 20, that says each element in the extension field can be written in a unique way as a linear combination of powers of A. C0 plus C1A plus C2A squared, etc., up through the n minus first power of A. P of X is your minimal polynomial here, and its degree is n. And A is the root that you are adjoining. And by the way, when I say adjoin, I hope you've realized by now that doesn't mean I'm just adding one element. I'm adding infinitely many elements. Okay? When I write this, it's not just adding one element to F. That was a point of confusion, possibly. You've got elements like this, where all these C's are from the base field, F. And what this means then, vector space-wise, is that the set of n elements, n vectors if you will, forms a basis for this F of A we're talking about here. This forms a basis for that field over F. Forms a basis for F of A over F. Which means, well, it's a linearly independent subset of F of A that also spans F of A, and that's what the other theorem emphasizes, that each element of this can be written in a unique way like this, as a linear combination. And that's a useful thing that you see. It's a helpful thing to be able to understand the algebraic character of elements of this field extension. Finite versus infinite extensions, you've got a finite extension in this situation when the dimension of F of A as a vector space over F is finite, as it is here. And the dimension would be n, the degree of this minimal polynomial. And the notation we would write is this. Similar to index notation for group theory, and in fact, we're going to, in lecture B at the end today, when we introduce Galois theory, we'll make this connection with the group theory notation a little bit more explicit, actually. There is a natural connection in the notations, and that's why they're kind of similar to each other with the group theory index notation. But here with field theory, this just means that this field as a vector space is an n-dimensional vector space over that field. That's subfield. And that's what this theorem up here about this unique representation was really implying. That's called a finite extension. Infinite extension, if there's no finite basis, it's still going to be a vector field over the base field, but no finite basis. Q of pi is still a vector space over Q, but it's not a finite extension. It's got no finite basis. Theorem that says finite implies algebraic. There's a field theory counterpart of Lagrange, but I think I better talk about that after the quiz. Let's take the quiz right now.